Yeah. Okay. Yeah. Well, thank you very much. Yeah, this has been lots and lots of fun. Okay, so we're finally coming back to the theorem stated in the first talk. Xn we had this degree n hypersurface in Cpn minus 1. This divisor sitting inside here. We had this yn tilde I think I used a small q for this actually. We had this group acting on yn tilde, and the theorem was that the split closed derived Fukaya category of Xn relative to D is A infinity quasi-equivalent to the bounded derived category of G equivariant coherent sheaves and Yn tilde after a formal change of variables in the coefficient ring. This was a A infinity quasi-equivalence over this field. All right? And the way we did this was we had this cover on this side. We had this algebra the endomorphism algebra of a single Lagrangian in here. Then we looked at A tilde, which was the subcategory up here, which is the union of all lifts of this Lagrangian downstairs. I guess I should have written these on the other side. And what we did was over this side, was we took this simplest matrix factorization, or the matrix factorization corresponding to the skyscraper sheaf K. We identified these guys up to a change of variables in the coefficient field. We passed from matrix factorizations to graded matrix factorizations, which by Adam's talk just now is the same thing as the bounded derived category of coherent sheaves on yn tilde. And this guy corresponds to these guys. So there was K down here. Shifts of K correspond to these guys. And then, so here, like the one guy downstairs turned into n guys upstairs. So this is something kind of like a Z mod n cover. This guy, for every sheaf in here, so all these guys can be made equivariant with respect to this group action, but they can be made equivariant in a bunch of different ways. So anytime you have an equivariant sheaf, you can tensor it with a character of this group. And so the number of characters is n to the n minus 2. The character group is this guy. So that passing between this guy and this guy up here is sort of like taking a Z mod n to the n minus 2 cover. And over here, this is a Z mod n to the n minus 1 cover. So here's what we have. So I just want to make it clear that this cover up here was broken into 2 stages, and this is kind of the steps that were happening in this commutative diagram of the grading groups that I had in the last talk. So what have we achieved? We've picked out some subcategory here and some subcategory here, and we've identified them. We also saw in the last talk
what I see you identify is in the morphism between some objects.
Yes.
Now, so when you say subcategory generated by this object.
Yes.
Okay.
So
yes.
You're saying that kind of you identified with like modules over these
So I'm taking the full subcategory generated by these objects.
And it's completely
Yeah. Does that answer the question?
It just said that formula you can think about it as a category of models over A. Like if A is over A tilde. Like formula you can think about this category as category of models, you know.
I can think of.
Like from of models over A.
Sure.
That's the formula way to say that.
Okay. Okay. So what we've done is we've identified two full subcategories, one on each side. In the last talk, we saw that the objects, so if you take this guy and look at its lifts to these objects up here, we saw that they correspond to this valence and exceptional collection, which split generates this guy. And you can use a similar argument to show that the lifts up here split generate this guy. So now we have a split generating category on this side and some full subcategory on this side. And if we prove that this guy split generates this one, we will be done. And that's what I'm going to do in this talk. And the way we're going to do that is using the split generation criterion that Cedric talked about yesterday. So remains so we have two maps. So the maps look like this, where QH star means quantum cohomology, which is the cohomology of X with coefficients in this field of formal Laurent series. And this is an algebra whose structure coefficients, so it has an algebra product called star sub Q, and to define it, you choose cycles Poincare dual to classes alpha and beta in cohomology. Then you count J holomorphic spheres U with 3 marked points, 2 constrained to lie on the input cycles Poincare dual to alpha and beta, and the third sweeps out some new cycle and you define that cycle that it sweeps out to be Poincare dual to the quantum cut product of alpha with beta. When you weight this by Q to the intersection number of U with D.
Now, are those maps algebra maps?
Yes. Well, this one is.
Yes.
And furthermore, this CO map is an algebra homomorphism intertwining the quantum cup product on quantum cohomology here with the Yoneda product on Hochschild cohomology here. Okay, this one turns out to be a QH star module map. So Hochschild homology is a module over Hochschild cohomology, but we're not going to need that. So, yes, Nati? It's a Hochschild homology is a module over Hochschild cohomology, therefore a module over quantum cohomology via the map CO. You could probably, well, you can think about it in various ways. Yeah. So maybe I should give the definition. This is quite similar to what Cedric talked about yesterday, except here we don't have all these non-compact Lagrangians and wrapped stuff and symplectic cohomology. We just have a compact manifold and the output, so instead of having this puncture which is asymptotic to an orbit in the middle, you just have a marked point in this, so you count J holomorphic disks with boundary conditions given by this chain of generators in the Fukaya category, its intersection points, and with an internal marked point, and that internal marked point sweeps out some cycle which is Poincare dual to this open-closed map. And you also have to weight these guys by Q to the U dot D. CO of alpha, where this is in quantum cohomology. So this is a Hochschild chain. So it's meant to take in some number of inputs and spit out an output. And this looks almost the same as this guy, except you regard this internal marked point as the input of your map. And
the same configuration, but just
you just change which things are inputs and which are outputs. Yeah. And again, so it looks like this. And from these pictures, you can well believe that you have, that these maps are dual. So if you take Poincare duality, mapping quantum cohomology to its dual, then you have a commutative diagram like this. This is probably V star plus n or something. So in particular, so the fact that you have an identification between Hochschild cohomology and the dual of Hochschild homology of your category is something to do with the category having a Calabi-Yau structure, which means Hom from L to K is the same as the dual of Hom from K to L, because they're both counting the same intersection points. But the crucial point is that this map, this diagram commutes, so up to identifications of the domains and images, CO is dual to OC. So it's a theorem. It's an extension of Abu Zaid's theorem that Cedric talked about.
In which generality we have the Hochschild homology or dual homology?
When the category admits. Yes. So the hypothesis is that you have some full subcategory of the Fukaya category, and the open-closed map, defined by counting J-holomorphic disks like this, hits the identity in quantum cohomology, just the fundamental class of the manifold. And the conclusion is that this subcategory split generates the Fukaya category. So that's what we want. This is what we want to use. How am I going to be for time? So I think I'm actually going to have enough time, so maybe I can just insert a little bit of motivation about what split generation kind of means in the Fukaya category with two examples and what the criterion means. So first, so suppose I'm looking at the torus, Fukaya category of the torus, and I'm looking at these two Lagrangians. So if you take these two Lagrangians and take the cone on the morphism, which is the direct sum of these two morphisms, what taking the cone corresponds to geometrically is kind of resolving them. Like this. And this has an analog in higher dimensions as well. Okay? So here is something that we got by taking the cone onomorphism between these two Lagrangians. So this Lagrangian I've drawn is generated by the two original ones. But now you can see the result that we've got is disconnected. It contains this guy and this guy. So this Lagrangian here is a direct summand of the cone that we just took. So this Lagrangian is an example of an object that is split generated by the original two guys, but not generated. So that's kind of where the taking formal direct summands comes into the picture. The second thing I wanted to say about the generation criterion is that the simplest Hochschild homology classes you could hope for are just classes which are, so here that instead of having P0, P1 all the way through PD, you just have P0, just one endomorphism of a single object. So that looks like this. So suppose this map hit the identity in quantum cohomology. Then for any other object K, this map hits the identity, and this map is unital, so this map hits the identity. Now this commutative diagram that Cedric wrote on the board, in this simple case, looks like this. This is what he called the coproduct, and this is just multiplication of these two guys to get an element of that in the category. So the commutativity of this diagram is seen by looking at this family of holomorphic annuli, which interpolates between this extremely thin family, which ultimately breaks at this point. And this side looks like, so the outside is L, the inside is K. So this side looks like this coproduct that was drawn like this yesterday. That's this side. And this side just looks like this mu2. It looks like that. At the other end of this moduli space, you have OC followed by CO. So this is when you think of this as a cylinder, and the cylinder just gets infinitely long and ultimately stretches and breaks. And it turns into a composition of OC, that's like this disk, joined at this node to a disk giving you CO. So that's roughly the argument that this diagram commutes. And then if this map hits the identity, then that means this map hits the identity, which means this one does by commutativity. In particular, this map hits the identity, which means you have P and Q in here. So that P maps from K to L, Q maps from L to K, and their composition is the identity. So this means K is a direct summand of L. And this generation criterion is some massive souped up version of this where you put Hochschild chains here, and instead of constructing K as a suband of one object, you construct it as a summand of some twisted complex. Okay. So how are we going to verify the hypothesis of this generation criterion in our example? Well, since the identity lives in degree 0, we really only need this map to be non-zero, surjective. This has rank 1. And this map is dual to the closed open map in the top degree, 2n. So it suffices to show this map is non-zero, since this is rank 1. So this hits the identity if and only if the map is non-zero, if and only if its dual is non-zero. So how can we get at that map? Well, the first thing we have is a lemma that when you take the class in degree 2 cohomology, Poincare dual to our divisor, and hit it with closed open map, you get the class in Hochschild cohomology that you get by differentiating the A infinity structure map mu. So recall an A infinity structure lives in degree 2 Hochschild cochains on our space and satisfies mu bracket mu equals 0.
Sorry, I don't understand the statement. Because left part depends on the divisor,
Yes.
and right doesn't.
Well, A is living in the Fukaya category of X relative to D. So our A infinity structure brackets to 0, which means when we differentiate it, brackets to 0, and then using the product rule, that means the Hochschild differential applied to Q d by dq of the A infinity structure is 0. So indeed, this is a well-defined Hochschild cochain. And the proof is that CO of the divisor is the same as counting holomorphic disks with a whole bunch of inputs and an output, and this marked point constrained to lie on D. And this is just equal to the number of times this disk hits divisor D times the number of such disks. So because D is a divisor, it's complex codimension 1, so it's going to hit, any holomorphic disk in a bunch of isolated points. Okay. And now we always have to weight our moduli spaces by q to the power of how many times of the intersection number. And this is, so taking this factor out the front is the same as taking
when you say number of times,
yeah.
if you're not in a complex reality, so why do you get intersection only have positive?
It's sufficiently close to being complex, yeah. Okay, so the point is that this number of points where this guy where D could have hit the divisor is equal to the intersection number. And since that's what we weighted our curve, the power of Q, we weighted our curve by, when we hit it by Q D by dQ, a factor of that intersection number comes down. Does that make sense?
That is due to the fact that the divisor has normal crossing, or it's kind of ordered?
So really in this case, we have, when it's normal crossings, you would better say DI, and you would better put QI D by dQi in here. Yeah. Okay, so now we got a bit of non-trivial information about what the closed open map does to one class in quantum cohomology. So since this map is an algebra homomorphism, which I haven't explained to you, but it's essentially, well, it's the same as this proof I gave yesterday about how the deformation class changes when you orbifold. You look at this moduli space. It has one degeneration where a holomorphic sphere bubbles off, and that's your quantum product. And it has another degeneration where these guys move apart, and that's your Yoneda product. And whatever comes in the middle gives you a homotopy between them. So that's a very quick proof of this. So now using this fact that CO is an algebra homomorphism, Sorry. So it suffices to prove that CO is non-zero in the top degree. So here's an example of a top degree class. You take your class in degree 2, take it to the power n, so it lies in degree 2n. So it suffices to prove this guy is not equal to 0. And this guy is equal to the top Yoneda power of q d mu by dq in Hochschild cohomology. So now we've really reduce this question to something we know we can solve, because this is a question just about our A infinity algebra A tilde. So you take whatever your A infinity structure is, differentiate the structure maps, take the top power in the Hochschild cohomology, and check if it's 0 or not. This is just algebra now, no geometry. So, lemma, if you take this A infinity algebra A tilde that we've computed explicitly, compute its Hochschild cohomology, compute this class in it, take the nth power, then it's non-zero. So now we're done with the proof of the theorem. And I guess I've got 10 minutes, so let me comment on two things. This?
No, sorry, that one,
Yeah.
That's because of duality, or?
That's because this equals that.
Oh, sorry.
Yeah. This is a result of the fact that CO of D is equal to this. So CO of D to the power n is equal to this to the power of n, since CO is an algebra homomorphism. So this is a rank 1 vector space. And this is a map of vector spaces. So if it's non-zero, it's surjective. So No, this one is one-dimensional.
Yes, I know.
So if this map is non-zero, it's surjective and therefore hits the identity. It's non-zero if only if its dual is non-zero. So the next question is, now that we've proven this relative Fukaya category is isomorphic to this category of coherent sheaves, what about the absolute Fukaya category? So the relative Fukaya category had some very restricted set of Lagrangians that it allowed into it. There's exact Lagrangians in the complement of the divisor. So for a start, it's defined over a different field. Called the Novikov field. If you restrict your set of Lagrangians, you can take it in Q. So this field that we're forced to define it over is like formal Laurent series in Q, except the powers are allowed to be real numbers. But they still have to, they're not allowed to accumulate at a finite point. They have to go to infinity. So I should say we should have. So this one, I mean, this Fukaya category, whatever it is, will be defined over this field, but there's not a definition in the literature yet. Fukaya O, Ota, Ono talk about the case where you have a single Lagrangian, and then if you have two Lagrangians, they construct a bimodule, but they don't construct the complete thing that arranges for all possible non-transverse Lagrangians and everything. So,
let me understand. On the left, objects correspond to exact Lagrange.
in the complement of D. Here,
So how would it be? Now, tensor products change objects,
no. Tensor product
change form,
just means
morphism.
changes the morphisms.
So the claim is somehow any Lagrangian is equivalent to some computation of exact Lagrangian itself.
Yes.
So this is the basic thing.
This is what we would like to be true, but we need to assume certain properties of this category that hasn't been defined yet to see why that should be true. But they're reasonable properties. So they're properties that if it doesn't have them, then maybe you didn't have the right definition.
But if you take Lagrangian, which was homologically has non-trivial intersection, how would you push it to complete?
There's no geometric argument like this. This is an algebraic argument. Sorry, there was another question?
Yeah, what is Q mapped to on the left? I mean, you have all these QIs,
So we already, maybe I did it kind of quietly, but we changed coefficients from this big ring that had all these lovely gradings on it that allowed us to compute everything explicitly to a field that allowed us to apply split generation results and Orlov's theorem and so on. And this map sent Qi to Q.
So what are the properties?
So what you would like is that so since you have some inclusion of categories, you have an inclusion of their Hochschild homologies. And you would like this map to commute, which should be true just because they're defined the same way. And part 2, the split generation criterion that I mentioned before, should also hold for the absolute Fukaya category of Xn. And I should say that constructing this Fukaya category with including all possible Lagrangians and perturbing them if they're not transverse or cleanly intersecting or whatever, and also proving this split generation criterion is work in preparation of Abu Zaid, Fukaya O, Ota, and Ono. So there are claims that these properties, will be verified in the future. So, and now it's kind of clear that since I found some objects such that this map hit the identity, I mean, in particular, when you regard them as objects of this Fukaya category, they also hit the identity and therefore split generate by the split generation criterion. So, there shouldn't be any new computations to do when you pass to this Fukaya category. Just making sure you build the theory well enough. So I wanted to make that point. And, well, I guess I'm out of time, but I just want to state, in fact, this is joint work with Tim Perutz. That if you have X and Y that are Calabi-Yau, and this Y, which is some family over the formal punctured disk, has what's called maximally unipotent monodromy around the origin of the formal disk. And if this guy split generates,
This guy means which Lagrange?
This is a completely general statement. So the hypothesis is that you've found some Lagrangians and you've identified with them with some coherent sheaves, and the coherent sheaves split generate. And the conclusion is that A also split generates. And the way you prove...
And the morphism of A is included in the morphism.
Yes. The full subcategories are quasi-isomorphic. Okay, so, and the strategy of proof. So you do exactly what I was just explained about trying to verify the generation criterion, and that turns into a question about whether the top power of this derivative of the A infinity structure map vanishes or not. So since these categories are equivalent, you can translate that into a question here, and then translate that into a question in Hodge theory on Y, and it turns out to be equivalent to this maximally unipotent monodromy condition. So this thing looks like you're part of the way to proving homological mirror symmetry, but actually it means you're all the way. So what I was explaining today kind of has a big generalization. Okay, so let me stop there.
Are there any questions? Well, I'll ask one question. So, this computation of functional cohomology, like what goes into that?
So you know, so Hochschild cohomology of the guy upstairs, if you take the equivariant part with respect to the covering group, that gives you a part of Hochschild cohomology downstairs. So it suffices to compute that. And downstairs, you know that you have this exterior algebra together with a deformation of the A infinity structure. So you can compute the Hochschild cohomology of the A infinity algebra by looking at the spectral sequence, you know, where the first page of the spectral sequence is just Hochschild cohomology of the exterior algebra, which you know by HKR, and then you control what the higher differentials can be, you quotient by some explicit thing, and then you just need to do Grobner bases and show this ideal that you're quotienting by doesn't contain this top power.
Just to repeat, it's the relation of the last theorem, the conjunction, the Verusian conjunction. This last theorem which you said, what's the relation to the homological Verusian conjunction?
So you might be trying to prove homological mirror symmetry, which would mean the Fukaya category of X is equivalent to coherent sheaves on Y.
I think it's enough to prove the downstairs.
Yeah, I'm saying, you've found some part of it, and the theorem is that that's enough to get all of it.
Yeah, but which generalized as, like for which point does this hold? Like for which X after the
Yeah, X. Yeah, this relies on them being Calabi-Yau and also on Y having maximally unipotent monodromy. So there are other examples of homological mirror symmetry you would like to prove where this doesn't apply, but.
So you're saying this is an approach, this approach can go more than mixed.
Yeah, this is something that, it tells you how much work you really need to do to, that it's the final step in the proof. So now you know that, you never need to think about the final step.